I would like to introduce TI's new advanced video graphics system. It comprises two 9995 microcomputers and uses state-of-the-art 64K DRAM technology. The demonstration you will see is that of a prototype which will be made available on all TM90 formats. The primary design objectives were threefold. Firstly, to ensure durable design activity over several years, a state-of-the-art system had to be designed. So the architecture is designed to grow with the user. We shall be demonstrating today a 512 by 512 pixel system, which can be easily expanded up to 1K by 1K pixels and beyond. Other features, such as scrolling in X, Y, or both axes, and zooming, ensure a durable design activity. The second key objective was to maximize the ease of use. For our target marketplaces, the maximum ease of use we consider to be absolutely paramount. So, from primitive firmware routines, we have hooks into both development time and runtime component software written in microprocessor Pascal to speed the development of everything from complex industrial mimic panels to advanced video games. Our third objective was to ensure an acceptable cost to the marketplace. This was achieved not only by a stringent design to cost exercise at system design stage, but also providing a cost versus performance trade-off capability in the system. Thus, a basic industrial system can be purchased at approximately 2/3 the cost of the all singing and dancing version with sprites. Now I'd like to go straight into some more of the details of our new advanced video graphics prototype.
Thank you, John. What I'd like to do now is run through the features of our graphics function. And I stress it is a function. It's not just a hardware system and it's not just a suite of software. But by combining the two, we have produced, in line with our functional strategies, a graphics function. We see here at the top of the screen, this prototype is based on a 512 by 512 pixel map. We've chosen this resolution to start our development work as it is approximately the limit of resolution in the horizontal direction which you can achieve on a standard TV tube. And as one of our major objectives is to maintain the overall cost of the system at a very low level, this is obviously a prime consideration, i.e. to keep the cost of the monitor to a reasonable level. Of course, as well as the 512 by 512, there are a number of other resolution options which are you can have up to 16 different colors on the screen. We then have reflection in X and or Y, which means in X we can change the picture and reflect it in that manner, or in Y we can invert it in that manner. Of course, an offshoot of having zoom and scrolling is that we can do panning, i.e. pan over any memory size you like, displaying, for example, a 512 by 512 area. We have inbuilt with the system an external video input, allowing you to, for example, add captions over a standard TV picture. One of the very innovative features of the system is its high data rate, the speed with which you can get data in and out of the memory. This actually comes out to be 800 nanoseconds per pixel when you are accessing it as RAM effectively, i.e. doing a random access. If you have video data in standard serial video formats, then the system will accept this data at video rate. In other words, we can use this system to do picture acquisition. Another offshoot of the very high data rate is it allows the system to have a sprite capability in conjunction with this pixel map. This again we'll be seeing later in the demonstration. We've just been through what amounts to a brief list of the hardware functions of the system. And what they add up to is a very, very clever and a very complex piece of equipment, which, unless we take steps to do otherwise, becomes quite difficult to use. So what we have produced is a corresponding suite of software which is dedicated to making the system easy to use. And we have some of the basic features of that software listed here. In the main, this ease of use software is dedicated to drawing shapes and then manipulating once they've been drawn. All of the captions you've seen so far and all of the text have actually been produced by the system itself. So what we've done now is to pull back slightly to see a bit more of the system. In this shot we've got the actual screen we've been looking at over the past 5 minutes, and also the VDU, which is displaying a menu illustrating the ease of use software. If we have a look down there, we've actually typed in H for help, and it's given us a menu of all of the commands which is available to the user at the moment. I stress this is a very preliminary demonstration orientated set of commands. This is not meant to be representative of what will be finally available. There'll be far more features than what we have here. But it gives you an idea of the sort of commands, the sort of high-level commands which we can use. Let's have a look down them. We've got commands relating to background color, sprites, which we'll come on to later, changing color, drawing various shape blocks, vectors, sprites again, reflection that we mentioned earlier, and scrolling, and color tables and characters, and also various other different commands. Now, for this part of the demonstration, what we've done is to digitize a picture and enter it into memory. So if we can now see the picture on the main screen here. For this scene, we've used the 4-bit planes, i.e. the 16 different levels, to produce an ordinary grayscale. Now, we needn't interpret the data stored in memory as just a grayscale, obviously, in that we can change it and interpret it any way we like. Here we're producing a number of different colours, and it also illustrates the number of basic colours, which was 4096, which you are allowed to select from for the actual final output colour. Again, interpreting it as a black and white grayscale. And one of the features that we showed earlier, a feature of the hardware, was its ability to do zoom. So if we zoom in on, for example, the top left-hand corner, we can now see the tree and parts of the building in much more detail. And of course we can do it again. That's actually a zoom by 4, and we're now seeing the pixel structure very clearly. And see that the whole picture is stretched out in X because we've got a zoom factor of 2 in X and 1 in Y. Again, we're going a bit further now and we see this tree stretched out quite considerably. See if we can now go back to the normal state. Here we've scrolled the picture along. You can now actually see where the picture started. Here's the tree and here's the building. That was normally completely on the right hand side and that was on the left. So we've scrolled and wrapped round. We've done it a bit further now and moved the whole picture around by about 180 degrees. We now put it back in X and we can start and scroll in Y. You see the X has gone back to usual and we've wrapped round and scrolled in the Y direction. Now we've changed the Y scroll again. Now there's the bottom of the picture and there's the top. And go back to begin again and we're back to the original state. Another feature was that we could invert the picture. We can invert it in X and we can invert it in Y. We'll start off, we inverted it in X. Now you see the trees on the right hand side and the buildings on the left. So we can see various parts of the picture as required. Of course we can pan by large increments as we're doing now, or we can pan by small increments. And we're just, in this case, moving it by 1 pixel at a time. Or we can go back and move it by 10 pixels at a time. Once again, all we're doing is examining the same data in memory. We're not changing the data, we're just reading it out differently and looking at different parts of it. And that again is just based on the hardware features of the system. What we want to do now is remove this picture, wipe it clean, and again we've changed the color table such that that particular background color is blue. Now what we're going to do is get the 95 that's in the system to draw some vectors for us. We'll just draw a vector on the screen. As you can see, it's extremely fast. If we just draw a few more fairly arbitrary vectors to show what can be done. And then perhaps one more. All these vectors have been defined by giving the system the endpoints which are required. Then the 95 executes an algorithm which in fact works to an accuracy of 32 bits to draw the vector between those 2 points. What we can do now is invoke another of the firmware routines, by which we mean features which are produced by software written for the 95s, which form an integral part of the system. And this one is text. Of course, what we can also do is change the color of the text, whilst writing any other characters we like. Here we've changed it to white and also added a bit more text in the top left hand corner. If we have a look at that, we can actually look at the character set a bit more closely, and perhaps if we zoomed one more time, you can now see it in quite good detail. Left. We can start creating shapes, as I mentioned before, by drawing vectors. So what we do is start drawing endpoints. We move the cursor to wherever we want. Then by hitting one of the keys on the keyboard, we cause the system to draw the vector between those 2 points. Then by ensuring it's an enclosed shape, we can get the software to fill it in for us. Now if we go somewhere else and draw another shape, see here we can draw shapes at any place in the screen, whether it be over an existing one or in quite a new position. In this case, we know that the background, the blue, is colour 4. So if we ask it to change colour 4 to colour 6, and we specify the limits over which is to search the memory, in this case we'll say we'll search over the whole screen, we can see it changing all of the screen. Now for this final demonstration, we've gone back to a clear screen and we're going to demonstrate sprites. Unfortunately, because this part of the demonstration is taken from an existing demonstration software package, we've had to put the system back into 50 Hz 625 lines. So there may well be some beat effects when looking at it at 60 Hz. Now what we're going to do is move across the screen a number of sprites which have been defined as numbers. And hopefully by watching carefully what happens, be able to see the concept of priority, where the highest priority sprites, and number 1 is the highest priority, always moves over sprites having a lower priority, in this case down to number 6. And from the movement, this should be illustrated. Here we can see all the sprites moving. Well, they're in fact moving one at a time. And they're moving quite quickly here. In the second section, we slow the sprites down. And we can see that the number 1 passes over all of the other ones. Likewise, 2 passes over the higher numbers, which are in fact lower priority sprites. But we will see under here, it passes below the number 1. Now this is done by manipulating data in the pixel map. So it shows the extremely high data rate which is achievable with this memory architecture, and also with the 95s. In fact, it's only by using the TMS 9995s that we can produce a system which is anything like fast enough to produce this sort of animation. Remember, moving the sprite actually means storing what was in front of it, writing the sprite, and producing movement in this fashion. Now here, we're actually redefining a lot of the sprites, i.e. we're turning them off and then changing the definition Again, it shows the incredible speed of the system. And finally, we're looking through all of the different color tables. We've got the same data, and we're just changing the color tables to give you some idea of the range of color which is available.
Well, I think we've seen from that short overview of the advanced video graphics system the tremendous power that's at our disposal now that we've got a TM90 graphics output function. I think you can see that we've met our three main objectives, which were firstly state-of-the-art performance, which will endure across several years of designing activity, featuring sprites, as you've seen just now, fantastic resolution, zoom capability, and all the other many features which we haven't had time to demonstrate. Our second objective, well, it's very difficult to show ease of use, particularly under the difficult conditions which we are working under now. But that too, I think, has been demonstrated. And work is continuing on the operator interface package to ensure the highest ease of use in order that even mediocre engineers can use this advanced function. Thirdly, cost. Well, we're confident in OEM quantities on TM90 format cards, we can achieve a volume AUP of well under $1,000. I believe this opens up new opportunities for TM90 on the basis of pure leadership and ease of use.
Here, we're actually redefining a lot of the sprites, i.e. we're turning them off and then changing the definition. Again, it shows the incredible speed of the system. And finally, we're looking through all of the different color tables. We've got the same data, and we're just changing the color tables to give you some idea of the range of color which is available.
Well, I think we've seen from that short overview of the advanced video graphics system the tremendous power that's at our disposal now that we've got a TM90 graphics output function. I think you can see that we've met our three main objectives, which were firstly state-of-the-art performance, which will endure across several years of design activity, featuring sprites, as you've seen just now, fantastic resolution, zoom capability, and all the other many features which we haven't had time to demonstrate. Our second objective, well, it's very difficult to show ease of use, particularly under the difficult conditions which we are working under now. But that too, I think, has been demonstrated. And work is continuing on the operator interface package to ensure the highest ease of use in order that even mediocre engineers can use this advanced function. Thirdly, cost. Well, we're confident in OEM quantities on TM90 format cards, we can achieve a volume AUP of well under $1,000. I believe this opens up new opportunities for TM90 on the basis of pure leadership and ease of use.